So, do you hear me?
Yes, we hear you. Yeah.
Okay, so we are live right now and Digital Davos in Davos, Switzerland during the World Economic Forum. Do you hear me?
Yes, we hear you. Yeah.
Okay, so we are live. Wow, wow, wow. Right now. Okay, so
Oh, there's an echo. I don't know if you hear that on your
yeah,
end,
I
Maya.
had to. Um, the YouTube was showing this 5 second delay, so it was going on.
Okay.
Okay, so thank you very much for joining me here in Davos for the second part of our conversation. How you see, we have a little bit worse of weather today. It's a little bit depressing, but so thank you very much for joining us. This time, I would like to reintroduce you. Maya, could you introduce yourself? And Christina, could you introduce yourself? So, Maya, please start.
Yeah, sure. Hi, my name is Maya Palakal. I am the co-founder and COO of New Root. I have a background in biology and philosophy, and I've been on the New Root journey for the past 5 years. When I met the core technical founder, Dr. Shakim Makawi, and I've been working alongside the rest of the New Root team since. During that time, I published pretty young, more on like the academic and scientific side before pursuing more of this entrepreneurial route. Yeah, and it's been great. I've had the great opportunity of working with some wonderful people and meeting some really amazing folks. So I'm looking forward to doing it and continuing as we move forward.
Thank you.
And I'll go
Christina.
now. Yeah, nice to see you again, Carl. I'm Christina Bjornstrom, co-founder and CEO of New Root. I've been in tech for really the last decade or so, as a co-founder, as a mentor, in several different capacities, but I've also ran a startup accelerator as well as served as president and executive director of the Swedish American Chamber of Commerce back in New England, or covering 6 states in the Northeast. The most recent thing that I did prior to jumping on board New Root full time is that I served as CMO and head of investor relations for Terranet, which is an autonomous driving software company based out of Sweden, that's publicly listed. And yeah, my background is kind of all over the place, but I've dabbled in investigative journalist, was also the youngest employee at Yahoo back in the day, so I'm aging myself by saying that. And been working on New Root at least, in the background for the last 7 years, officially for the last three, or as in full time for the last three. So very nice to see you again and excited to continue our conversation.
Thank you. So this time we want to speak a bit about the company which you have, Node, and to dive more in what Node is doing. And we believe that the intellectual property which you have surrounding the new training models and the methodology is really interesting, and we would like a little bit more to share about this development here in Digital Davos. So let's right away getting in and speaking about the how it's basically about this training models and how it functions. What is the difference between training it with your technology and training it with other technologies?
Maya, I'll have you take a pass at that.
Okay, cool. So I think the unique thing about Neward's approach is that unlike most, if not all of the other models on the market today or anything that you're really going to be finding, we do away with neural nets. So I think for the longest time since first really coming into conception in the 1950s, a lot of people have adopted the neural network approach, which is simply just taking a large amount of data, pushing it into the computer, and then kind of putting your hands in the air. Perhaps you've given the computer a few rules as to how to detect a pattern. But then afterwards, the computer is kind of left to do its thing, which is finding a pattern in a large amount of data. And of course, before anyone comes forward and says, okay, there are, several different ways of doing this or finding a pattern. All of that is to say that fundamentally at the bottom end of it is you take a large amount of data, push it into the computer with really little explainability or traceability, and then ask the computer to make a decision. The issue, though, is that while this method or approach is really good at one type of task or specific types of pattern recognition, it is not good overall at general tasks or used foundationally across the board for several different types of tasks. And I think this is why in critical decision making, especially when we're talking about things like health or non-civilian applications, this is where the topic of AI comes a little bit gray. And I think a lot of people are apprehensive about discussing it further. So this is where neuro comes in. So, again, based largely upon the work of Dr. Shiki Makawi and his training as a theoretical physicist and mathematician, he developed a model, a geometric model, where you can basically see how your data is being processed by the computer. And so data comes in, we map it onto this model. And then based upon how the model is reacting to that information, we can then use these type of reactions to categorize or, ascertain what the information is coming in.
Maya,
And
can you specify a little bit more on the model and the functional?
yeah, so for anyone who wants to go into the specifics and for the purposes of really delving in deeply, feel free to come to either Christina or I. But at least in terms of the functionality, I will say that we were inspired by the string theory, or at least, Shiki was inspired by the string theory in developing this genus 1 model. So that being said, I think the unique properties of this for anyone who's more on the theoretical physics side will know that, okay, yeah, especially when we're talking about different types of physics-based characteristics, that model or that approach, which he had published on several years ago, are very unique. But I think for using it in this type of application or for a silicon-based intelligence, this is where we really come into play and really, I think, set a new precedent for what's in AI and, therefore, downright machine learning. I think, oh yeah, sorry.
Right now, for example, for machine learning, when something has to recognize, okay, I should not put something with a brand logo in front, a class. You would have to go through different layers of pictures to see the class.
Yeah.
So how would it different in your application that you will not layer it, and how much computer power would you really save by doing it? And please.
Yeah, sure.
Already complicated enough, but like, well.
Yeah, sure. So yeah. I mean, to get really into the nitty-gritty of it. So if you're detecting an object or and thanks for referencing image recognition, because again, based off of the background and expertise of the team, this is really where that's kind of our foray. So typically in image recognition, you have to pass through several different images of an object multiple times. And that's just based off of the nature of how people filter images today. And in addition to that, you have to have several different types of images of the same object, so that for any one instance of that object or a random instance of that object coming in to your computer is able to detect it. Again, the issue with that, though, is that the vast amount of computational power that's associated with that, for the benefits that you're gaining from it, I think we're really seeing that conversation and discussion really liven up as time progresses, especially with the generative AI wave that we're focusing and kind of hitting now. In Neuroot's case, what we've done is we've gotten rid of a lot of those type of techniques that are typically used. For instance, in filtering, instead of filtering multiple times, we can filter in one shot. And we use that, we do that using our equation-oriented approach. I emphasize that because a lot, if not all, of things done in computer science today are based on a statistical approach. And so we don't depend largely on the amount of data that we're pushing into our computer. After cutting down on that filtering, or the old filtering technique where we can kind of filter in one shot and select what of the object that we want to filter, which again cuts down on 60 to 80% of the typical AI workflow. We can then map on basically that image onto our model. Because of the nature of our model, we increase the discriminative power to any one type of data that's coming in. And so by nature, what we're doing is we're cutting down on the amount of training data needed for our model. So
my question is, the training data is needed to for a model to learn to recognize something.
Mm-hmm. Yeah.
But when we go further in AI, is, you see, cutting down on training, but when you combine it, I know AI doesn't have association now, thanks God. This could be dangerous, but you see, cutting down, how much is really the and why we don't risk that the AI doesn't become unspecific in this moment when you cut down on the training data.
Mm-hmm. Yeah. So for our prelim results, when we were, basing this off of the MNIST data set, what we noticed with, comparing it against standard go-to models is that we were gaining about like we were 50 times more efficient than your gold standard model for image detection. And that kind of was a good indication to us that, okay, at least, baseline for a new and upcoming model to be used, this is something that we're on the right track on. And that is pretty significant because typically, especially with larger companies, you're really trying to compete for at minimum 1 to 2% more computing power on any given task. So that in combination with cutting down on that 60 to 80% of data cleaning augmentation really ramps up the benefits of this model. And then in terms of, you mentioning, look, is there something where we would kind of become non-specific? Again, this is the nature or due to the nature of our approach, right? So because of the unique characteristics of our model, for any one data that's coming in, we're again increasing the discriminative power to that type of data. So we really don't veer into any non-specificity or anything like that, which you would typically find if you were trying to do the same thing with a neural nets-based approach. And that, again, is largely because today's models or today's approaches are a black box, regardless of those coming forward and, saying, we have increased traceability or increased understanding of our model. Ultimately, right, if something goes wrong and you want to go back and basically do some troubleshooting, you can't. But with our model, you can. And that's again based off of you really seeing how the data is being processed and being mapped onto the model, both for pre-stored data and data in real time. So that is why, because of the unique characteristics of our model and our increase in discriminative power.
Maya, I was also going to mention, sorry, apologies. I think it's also important to note that in certain situations, when speaking of training data sets and such, we have found that when it comes to certain types of data, we may only need even one sample, for example. And that's the case with some of the medical imaging stuff that we've been able to do. And in addition, we need to run far fewer training passes than I would say our counterparts. So then again, you're talking about significant or massive savings, energy savings, and computing savings, in addition to the fact that we're able to take in any kind of data in any combination in real time in streaming in any file format. So that again kind of deviates from the norm, but it enables higher discriminating power as well.
Thank you very much. Christina, Maya, we have our next panel already on stage here in Davos, so I apologize that we have to cut down now. And
no worries
we
at all.
appreciate it. Again, you have a really interesting company, and I hope to have you next year again as speakers. Thank you very much.
Awesome.